Mr. T here, and we have a tutorial today on square roots. We'll be talking about how to simplify square root expressions and how to use square roots to solve quadratic equations. So let's talk. Much of what's at the beginning here should be familiar with you. When we take the square root of a number, we're looking for a number that if you multiply it by itself, it gives the original number. Another way of saying that is if a squared, or a times a equals b, then a is the square root of b. So 2 would be the square root of 4 because 2 times 2 is 4. But also negative 2 is the square root of 4 because negative 2 times negative 2 is also 4. So when we take the square root of a number, there are two possible answers. We can have the principal or positive square root, and we can have the negative. This will come into play later when we talk about solving quadratic equations using square roots. The symbol, which sometimes we might call the square root symbol, has another name. It's also called the radical symbol. And when we have a radical symbol over a number in an expression, that means only the positive square root. So if I asked you to find radical 4, our only answer would be 2. If we wanted the negative square root of 4, we would write that as negative radical 4. And later in the tutorial, we'll be using this symbol here, plus over a minus. That means both the positive and the negative principal root or square root of 4. So that is just a way of representing two numbers in a compact form. So this means both positive and negative 2. Can we take a square root of a negative number? And the answer there is no, because to have a, if you take the any number and multiply it times itself, it's going to be a positive number. So positive times positive is positive, and negative times negative is positive. So there would be no way to have a number times itself to equal a negative number. There are two kinds, or not two kinds of numbers, but when we're talking about radicals, there's a class of numbers called perfect squares, which we'll be talking about a little bit more in a minute. And when we take the square root of a perfect square, we get a rational number, either an integer if our perfect square is an integer. It could be a fraction if our perfect square is a fraction, and we can also have decimals that are perfect squares. Most square roots are irrational numbers. So for example, the square root of 2, or radical 2, is this irrational number that continues on forever. Remember, irrational numbers cannot be represented as a fraction, as a rational number. And in terms of decimal, they never terminate, and you will never find any pattern of repeating numbers or digits in the decimals. One of the implications of radicals being irrational numbers is we cannot write an exact value of square root of 2 by writing a decimal. So if we use the calculator and get square root of 2, depending on your calculator, maybe it takes it out this far. But that's just an estimate. It has been rounded. It is not an exact value. Mathematicians like to provide solutions to equations in exact values. They can leave it up to the application to decide how many decimal places is appropriate. Some applications that we're doing, shopping, working on budgets, maybe we only need our answers to 1 or 2 decimal places. But if you're an engineer planning to launch, say, a rover to Mars, and we're trying to plan the flight and the trajectories, we need to take out a lot of decimal places in our answers. So as mathematicians, if we're solving equations and keeping things in radical notation, as it's called, then we are providing an exact answer. So our next part of the tutorial here is going to be talking about how do we work with numbers in this radical format. These are some examples of radical expressions. Most of the tutorial here we're going to be talking about ones that only have numerical values in them, but we can also have variables. And again, what we're going to talk about next is how we simplify them. The process of simplifying the radicals will make use of some properties that I've had here. So if we have the square root of two numbers multiplied together, we can break that up so that we take the square root of one number, the square root of the second number, and multiply them together. Now this does not work for addition. Oops. So if we had the square root of a plus b, this is not equal to radical a plus radical b. Be a common mistake some of you might make later, but we cannot split that up, so that is not true. But multiplication works, and same for division. We can, if we're taking the radical of a fraction, we can take the radical of the top and the bottom separately. We will also be using these two properties, which we've sort of already talked about and should be obvious, but we'll be using those when we simplify the radicals. So if we take the radical of a number that's a perfect square, or something squared, you get just that number. So square root is the inverse operation of squaring something. And if you've got the square root of something times the itself, that undoes the radical. Using this property over here, square root of a times square root of a would be the square root of a times a, which is square root of a squared, and up here we said that that was a. So let's talk about simplifying radicals. There's two things that we're going to do. We're going to simplify radicals, and then we're also going to talk about rationalizing radicals. We are trying to get the number underneath the radical symbol to be the smallest possible number. And the way we do that is we're going to be trying to factor out perfect squares. So you can read the words here. You can pause it if you need more time, but let's go into some examples. You'll see how this works out. When we're looking at a radical, so let's look at this top problem here, what we are looking for are any of these numbers. These are perfect squares. Now they're not all the perfect squares. They're the perfect squares up to 12 squared. We won't be using for radicals, but 1 squared is also 1, so that's a perfect square. So which of those numbers, in fact, what's the biggest of those numbers that divides into 18, and is 9? So we can factor this into radical 9 times radical 2. And we know radical 9, since that's a perfect square, is going to be 3. And then we have radical 2. So this is the reduced or simplified radical for this. If we look at 72, 36 divides into 72. So this would be radical 36 times radical 2. Square root of 36 is 6, so we get 6 radical 2. From the property on the previous page, we know that this is 7. Now here we've got a couple ways we can do this. We could multiply these together, so let's do it that way first. So we have radical 24. And then ask ourselves which of these numbers divides into that. So 4 divides into 24. So we get radical 4 times radical 6, which would be 2 radical 6. We could also split this up. It's divisible by 4, so we would get radical 4 times radical 3, and then we have times radical 2. This is 2. And we can combine those using our multiplication property of radicals to get our radical 6. Here we can split this up into radical 4 times radical x squared, and radical 4 is 2, and radical x squared using the property would be here. Now let's look at fractions. So again, what we want to do is, well, this one's a perfect square, but we want to split, the easiest way to see this is to split our top and bottom. This is a perfect square, so we get 6/5. Here the numerator can't be simplified. The bottom we get radical 16, so we would leave this as radical 3/4. And this last one we need to talk about because we would have radical 7, and on the bottom we have radical 4 times radical 2. So we get radical 7 over 2 radical 2. And in our next slide, we're going to learn that the rules of algebra, the conventions of algebra, it's not so much a rule, the conventions of algebra is that we do not leave radical symbols in the denominator, and we're going to talk about how we do that. That's called rationalizing radicals. So let's look at our next slide. So again, as I stated, our convention is that we will not leave radicals in the denominator. As we did in the last, we'll simplify our radicals first. And then the way we get rid of a radical in the denominator, so if we have a radical, say 2 in the denominator in our last problem, so after we simplify we have that, what can we multiply a radical by to get rid of it? And we saw from our properties we can multiply by radical 2, because radical 2 times radical 2 is 2. But if you have a fraction, you can't just multiply the denominator by something. But we are allowed to multiply the top and the bottom of a fraction by the same thing, because that's value of that is 1. So here we're going to get radical 14 on the top, and on the bottom we have this 2 times that, which is 2, or we would get radical 14 over 4. So that process we just did is called rationalizing the radical. So let's look at some more examples of these. Well, we just did this one. So let's look here. We're already simplified, so we just have to multiply by radical 3 over radical 3, and we get 2 radical 3 over 3. And then we can look to see whether that fraction simplifies. In this case, not. Here on the top, we can split 45 into radical 9 times radical 5. And 32 is divisible by 16. So now we have 3 radical 5 over 4 radical 2. And now we need to rationalize, so we're going to multiply by radical 2 over radical 2. And now we have 3 radical 10. And on the bottom we have 2 times 4 is 8. Now before we're done, we need to check two things when we have a fraction like this. We need to check, can this fraction here be reduced, in which case no. And we also need to see whether or not this radical that gets formed could be reduced, but there's no perfect square that divides into 10. Now the reason we've been reviewing these radicals is that we want to solve quadratic equations and radicals, and we're going to leave the answers in radical form so that we have exact solutions. We can solve quadratic equations, not all of them, but only certain quadratic equations. They have to have or be missing the term with just the x. So they can have an ax squared term in the beginning, and then they can have a constant. We can't have the bx. Our process, if we have an equation in this format, will be to get the x squared by itself and then take the square root of both sides. When we solve an equation using square roots, we want all the possible answers, so we'll be taking both the positive and the negative square root. So let's look at an example. So here we have no term with just x, so we can use square roots. We want to get this by itself, so I need to first subtract 1. So I have 2x squared equals 16. Now a common mistake would be to take the square root of here of both sides, but if we do that, this is not a perfect square, so we can't take the square root. So we want to get the x squared by itself, so we're going to divide by 2. And we have x squared equals 8. Now we're going to take the square root of both sides, and we need to take both the positive and the negative square root of 8. Here we get x, and here we get plus or minus, and we can split radical 8 into radical 4 times radical 2. So we get plus or minus 2 radical 2. Now we're not going to put that in calculator and round that to a decimal answer. We're going to leave the answer in this format. And this is what's called an exact solution. And but we will always attempt before we finish to reduce our radical using the techniques earlier in the video. So let's finish up with just a couple more examples and then we'll be done with this. So again, here we will add 7. So we get 2x squared equals 7. We need to divide by 2 because again we want to get the x squared by itself. So now we have x squared equals 7 halves. We square root both sides, both the positive and negative square roots, so we get positive 7 halves. Now we need to simplify this, so we're going to split this into radical 7 over radical 2. And can we leave it like that? And of course our answer is no, because we need to get rid of the radical in the denominator. And our final answer for this question, for this particular problem, would be radical 14 over 2. Again, we need to make sure you don't forget the plus or minus. For some of you, that'll be a common mistake. Here we subtract 9, and we get x squared equals negative 9, and we take the square root of both sides, and we get plus or minus the square root of negative 9. But we learned earlier that there is no real number solution for this, so this equation has no solution. The other day we talked about factoring difference of two squares, and I threw in a sum of two squares, and we talked about that being prime. Here's an example why. There is no value of x that can make this equation true. It also means it can't be factored. Our last example here, instead of having the x squared, we have a expression, but the process is the same. We want to get the part that's squared by itself, so we're going to subtract 3. So we get 2 times x minus 5 quantity squared equals 72. We're going to divide by 2, so we get x minus 5 squared equals 36. We're going to square root both sides, remembering to take both the positive and negative square root. When we square root this here, we get x minus 5. Square rooting undoes the square, and here this one happened to be a perfect square, so we get plus or minus 6. And we're going to add 5, so we get 5 plus or minus 6. Now we want to simplify this into two numbers, so what this means is the quantity 5 plus 6, which is 11, or 5 minus 6, which is negative 1. So these are our two solutions. If this had not been a perfect square, we would leave it in radical notation. So let's say this had been, I don't know, 73. Let's just rewrite it here. Let's make it a smaller number. Let's make it 35 maybe. Let's see how this works out. So let's subtract 3. So we've got 2. Now we're going to divide by the 2. I made this a perfect square again, so let's make this 33 here. So this is now 30. So I'm going to divide by 2, so we get x minus 5 squared equals 15. We square root both sides, so I get x minus 5 equals plus or minus the square root of 15. So again, we square rooted both sides and took both the positive and negative. Now this is simplified. There's no perfect square, so we get our final answer is 5 plus or minus radical 15. Now we'll just leave it in this condensed thing, but this again means two numbers, 5 plus radical 15 and 5 minus radical 15. So if we were converting this to decimal, we would have to calculate two different numbers. If this is a perfect square, then we want to go ahead and reduce it so that we can see the two individual solutions. So I hope this helps, and talk to you on the next video.